So let's discuss here how we go from one region to the other using the WKB approximation. This is a concept that is very important, and this is related to what we call WKB connection formulae. Let's have a look. So to consider WKB connection formula, we have to see what happens first in the region in which the WKB approximation is not valid, namely the classical turning points. And first, what do we do for idealized stepwise potentials? In idealized stepwise potentials, we apply boundary conditions when E is equal to V naught, is when we have that step in your square potential, right? Now, here, we have just derived these WKB wave functions, and what we can see is that when this happens, Px is going to be equal to 0. So when Vx is equal to E, or the energy of the particle, Px will be 0, which means that WKB solutions are going to diverge because they are proportional to the 1 over the square root of the momentum. So what can we do under such circumstances? How do we treat this? Well, the first and key point is that WKB solutions cannot be valid near the classical turning points because they diverge, right? So to connect the solutions, we're going to need a different approach in the vicinity of the turning point, but we need to retain the fact that the WKB is asymptotically valid. It has to tend asymptotically towards the WKB. That's what we're going to aim. So we need to find solutions in the vicinity of these classical turning points that converge to the WKB solution once you move away from it. And more specifically, let's see, for instance, what I mean. Let's suppose we have a barrier, okay? So this is Vx as a function of x. Here you have the energy, so of the particle. So this region here, this whole region here is classically allowed. This region here is classically forbidden. But let's assume that given our circumstances, WKB is valid only starting from a certain point here and another point here. And A is our turning point. So we want to see what we're going to do in the vicinity of the turning point, so that we come up with a solution that in the limit is going to tend to the WKB solution. And this is our motivation. So we know WKB solutions are asymptotically valid. They can be used only far away from the turning point, but we know as well that the exact wave functions, they are smooth and continuous for all x. Yeah. So it's a bit like what we had before, that we had a continuous wave function that was smooth as well, and you had all these stepwise type of potentials, and you have to match things. Now we have found solutions far away from the turning points, but we have to find ways of matching things in the vicinity. And we have to construct a wave function that is going to be smooth and that's going to be continuous for all x. So how can we join the two types of WKB solution that we have previously found across a turning point? What do we have to do? So the task that we have is we're going to find an additional family of wave functions which are valid at the classical turning point and which converge to the WKB solution away from it. This is what we want. Let's think about what we can do near the turning point. So near the turning point, Vx is approximately linear, right? Because what you can do is you can expand Vx minus E in Taylor expansion, and you get something like that. So it's an approximately linear function around the point, around the turning point, A. And you have this slope A, which is dvx gx at the turning point. Fair enough. So this is a constant. And this is an expression that gives you a potential that is linear. So this means that our time-independent Schrödinger equation looks like this now. So we have rearranged this, and we know that this is the solution that we'll be seeking. And to give you an example, if you have A bigger than 0, this means the slope is bigger than 0, this is going to be a right-hand barrier. So here you have classically allowed and here classically forbidden, and A is your turning point. And if A is smaller than 0, you have a left-hand barrier. So here classically forbidden, here classically allowed. For simplicity, we're going to consider A bigger than 0, so we're going to consider a right-hand barrier, and we're going to change the variable to make our life simpler, actually, and this is going to give us the area equation, whose solutions are known, and they are known as the area functions aiz and biz. They behave like this. So you see that aiz is kind of oscillating and then decays in some regions for z bigger than 0, but oscillates for z smaller than 0. And this other guy, biz, oscillates here also for negative z and is exponentially increasing for positive z. So we have these solutions, they look like this, and asymptotically, we can write them like this. So you have these expressions in terms of these fractional exponents of z, and divided by z 1/4, and you have this expression here when it's exponentially increasing. So they are symmetric if you flip the sign of the exponent up to an additional factor of 2. If you don't trust me, you can check it. I'm not going to prove it. Now, for large negative z, we have these kinds of expressions. You can see you have a cos, you have a sine, oscillating, as we said, and you have some kind of phase shifts here. And they are symmetric also on the flipping cos and sine, apart from the additional -1 factor in this expression here for biz. So we know how they behave asymptotically. I'm not going to prove this, so I'm going to state and I'm going to provide you some kind of heuristic explanation. There are several ways of doing this rigorously. This is not something we are going to do in this course, but one thing that we need to learn is how to use this formula. So these solutions, they are continuous across the turning point. They converge to the desired behavior, exponential growth or decay, and oscillatory behaviors in the classically allowed regions. And what we want to do is we want to manipulate the solutions so that they can converge to the WKB formula when you are away from the turning points. Details, if you're curious about how to do this nicely, I'm going, as I said, to do some kind of heuristic explanation, but if you are curious about it, have a look at Brunsden and Joachim, chapters 8 and 9. If you are a fan of complex analysis, have a look at Landau and Lifshitz. It's quite good. There are some cool contour integrals. But if you're not a fan, don't worry. Also, Merzbach has quite nice explanations for array functions, how you match them, but this is very clear and good enough for us for the moment. So what I'm going to do is I'm going to bring some kind of educated guesses, and I'm going to replace, because we know how the WKB formulae have to look like. So I'm gonna make some guesses, okay? You can prove this rigorously, okay? I'm just doing this because our time is limited and we have also constraints of what should be shown in this course. But bear in mind, this can be shown rigorously. So what I'm going to do in the expressions that I had before in terms of x, z, cos z, sine z, I'm going to replace z with this when z is equal to, is smaller than 0, which is the classically allowed region, and with this in the classical forbidden region, which is when z is bigger than 0. Actually, that's when you had this oscillation for the z smaller than 0. This is corresponding, if you do a mapping towards x, to our classically allowed region. Okay, and then we need to alter the normalization to obtain this kind of behavior. Can be done rigorously. I'm just going to put the result, but I want you to understand that you can also make some educated guesses and you can get the results as well. So the expressions look more or less like this. And this is for the allowed region and this for the forbidden region, psi A in both cases, whereby P and Q have been previously defined. Just have a look at our previous slides. And similarly, we find this expression here. Psi B is another solution in terms of BI for the allowed region, and this for the forbidden region. And the general wave function would be a linear combination of psi A and psi B, which would then depend on our boundary conditions. And what we need to do is we need to consider the limits of psi AX and psi BX for large x. Take, for instance, x going to plus minus infinity, and these limits, they have to match the WKB expressions. So for the classically allowed regions, if you do that, you get this and this. Here, put A. I don't know why it's C, but let me annotate. This should be A. This should be A because that's our turning point. And for the classically forbidden region, it's not moving, this guy. For the classically forbidden region, let me get rid of this. Shouldn't be there. We have then this exponentially decaying wave function and these exponentially increasing wave functions. Now, how do we match these solutions at each side of the barrier? Okay, we haven't done the computations, but according to these results, what we had is we had some wave functions which were derived and computed for a linear potential, which is what you have in the vicinity of the turning point. These wave functions are made to match or are constructed then in such a way that you obtain asymptotically something that looks like the WKB approximations, functionally speaking. And we know that these should be, in general, they're going to be given by coherent superposition of psi A and psi B in whatever region you are. So how do we match this? Well, here once more, I'm giving you the solution. So for a right-hand barrier, if you have this solution on the classically allowed region, you should have this one on the classically forbidden region. So you have a cos here, and then here you have an exponential. And if you start from the classically allowed region with a sign, here see you're integrating from x to the turning point, here as well from x to the turning point, then you get here an exponentially increasing wave function. Notice these arrows are going to discuss. So these arrows actually indicate the direction which is safe to apply this solution. Obviously, this is going to depend on the boundary conditions that you have for your problem. But usually, if you have these exponentially decaying wave function, it's safe to say that the corresponding wave function in the classically allowed region is going to give you this. Whereas if you consider here this exponentially increasing, you don't know if you're going to have a sign or you may have something else. So you have to proceed with more caution. Whereas if you have a sign, you're definitely going to have this. We're going to see this in more detail right now. And for the left-hand barrier, you have on the left-hand side an exponentially decaying wave function, which is going to give you some oscillating on the other side of the barrier. And if you have a sign, you end up with an exponentially increasing wave function on the left. So here is a left-hand barrier, which is classically forbidden to classically allowed. The one before was a right-hand barrier, classically allowed to classically forbidden. And coming back to the arrows indicate the direction for which is safe to use the connection. And the reason is that many times you have some very small contributions from exponentially increasing or wave functions, which are going to mask exponentially decaying wave functions, and they are going to lead to the wrong solution in the classically allowed region. Remember that in the classically allowed region, you're going to have oscillating wave functions, cos or sine. The phases also are going to depend on the problem, right? But in the classically forbidden, you can have something like this, for instance. You have an exponentially decaying wave function which is multiplied by 1000, and you have an exponentially increasing wave function which is multiplied by 0.01. I mean, it's clearly that psi b is going to dominate very quickly, although this coefficient is small. And what is going to happen is that neglecting this guy is going to lead to incorrect results in the classically allowed region, because this will give you an oscillating wave function in the classically allowed region and this as well. So you really have to be careful with these types of things. And I'll stop sharing now. We are going to see then a few applications, which is the next topic, in which hopefully you're going to see how we can use these in physically relevant problems, such as transmissions in a barrier, or to calculate the energies of a potential well. Even for quantization conditions, we can use WKB approximation. So thank you for watching, and see you in the next clip.